So in the previous class, we considered the Smith chart basics. We derived the equations related to the Smith charts and the various circles they are present on the Smith chart, right? As we know now, there are two types of circles. One set of circles are constant resistance circles, and we can see them like this. Okay, and second set of circles are called as the reactance circles. They are going to represent the reactance of the load resistance. Okay, reactance of the load impedance. Sorry. Right. Okay. Then we try to represent some of the points on the Smith chart. Right. Okay. Right. So today we'll start solving some of the problems based on the Smith chart. Okay. To start with the first problem. Problem number 1. A 0.1 lambda length transmission line has the characteristic impedance has a characteristic impedance 50 ohms. The characteristic impedance of the line is given. It is terminated. It is terminated with ZL equal to 5 plus J 25 ohms. Okay, so 5 plus J 25 is the this. So we have certain questions related to this. Part A of the question. What is the impedance at L equal to 0.1 lambda? Part B of the question. Find VSWR. Okay, then part C of the question. What is the reflection coefficient? Okay, and find the gamma, that is reflection coefficient, at L equal to 0.1 lambda from the load. All right, so these are the questions to be answered. Right, so just note down what is given. Length of the line is given, which is 0.1 lambda. It has a characteristic impedance, so Z0 is given. So Z0 is how much? Z0 is equal to 50 ohms. Okay, ZL is equal to 5 plus J 25 ohms. Right. Okay, now, so I'll solve here. You also solve on your Smith chart. Okay, I'll bring up the Smith chart onto the screen now. Just 1 second. All right. So from the data given, I need to have a normalized ZL. So you see the small letter ZL is capital ZL divided by Z0. Correct? So we can, from the given data, this is 5 plus J 25, divide that by 50. Just to calculate the ZL normalized value, 5 by 50, that is 0.1, plus 25 by 50, so that is 0.5 ohms. This is the normalized impedance. So always what we do, we solve with the help of the normalized impedance only. So first step is to calculate the normalized impedance. So once you find that, right, you need to mark that on the given Smith chart. Okay, so we know how to mark this, right? I just have to look at the real circle, right? That is 0.5. Is it 0.5? No, 0.1. So 0.1 is, I think, this circle, and 0.5 I need to find out. 2, 3, 4, 5. Okay, if I'm right. So this is the point. Correct me if I'm wrong. Just check. So this is the point. 0.1 plus J 0.5. Okay, right. So that is the first thing to mark anyway. Right, so that's the point. That is ZL. I'll just mark the ZL over there. Right, so I want to find out in my first part of the question, what is the impedance at L equal to 0.1 lambda? Okay, so that means this is at the load. Okay, at the load impedance is given by this. So the question is, what is the impedance at L is equal to 0.1 lambda? Means I want to move away from the load. Correct? So just let's consider the transmission line once. So see, this is how the transmission line looks like. So they have mentioned that there is a ZL here, which is given, right? And the Z0 of the line is given. Now we are moving from this point. I have to move how much? I have to move 0.1 lambda away from this. So at that point, what is the impedance they are asking? So you see, I have to move 0.1 lambda towards the generator, correct? This is the load. This point is the load. From the load, move towards the generator. So you can see something written over here. You read this and also you try to read this, because they have written something and they also have given a direction. So what they have written and what is the direction, both are important for us. So right now I am at the load, and if you consider this here, maybe it's I don't know whether it is visible to you or not. You may have to zoom a little bit. This is the direction. It's a direction given. Okay, I'll try to zoom it. Let's see whether we can see that. So can you see? It's written like wavelength towards generator. And I can see that the arrow mark is this way, over here, right? In the sense, if I move clockwise, that means I am moving towards the generator, and whatever numbers written here, right? 0.04, 0.05, 0.06, it is increasing. In a sense, the length is increasing in terms of the lambda. Okay, it's like 0.04 is in terms of lambda, 0.04 lambda, 0.05 lambda, and so on. Okay, so that's what is the lambda. So now you see how what is the distance that I need to cover? The distance that I need to cover is 0.1 lambda. Okay, fine. So in order to do that, what I want you to do, you should mark, let me change the color. You will use a scale to mark the origin and connect. Let me do it again. You hold, you make a connection in this fashion. Okay, like this. Draw a line from origin passing through my point and extend this away. Okay, when you extend that away, you will read a value over here, right? Or here, anything is fine. Okay, whatever value you read, right? Let me zoom it to see what value we read in this problem. Okay, I think we read a value 0.75, 0.075, correct? So I have to rotate clockwise because I want to move towards the generator and add a zero point 0.1 to this. There is what's the value? The value given is 0.07. So add 0.1 to that. I think I my mistake. I need to add 0.1 lambda, correct? So this value is 0.07. Uh, so you have to reach 0.17. This is 0.075 lambda. I need to add 0.1 lambda to that. Yes, right? So that means I need to move that much amount. Okay. So what we'll do, I'll go further on this side and I'll mark the point 0.175 over here. Okay. So maybe the 0.17, this is 18175 is this point, correct? Right, 1 7 and 1. You look at the outer side scale. Okay, the inner scale is for the ones which is rotating anti-clockwise. Okay, all right, so consider that as the point and draw the straight line connecting that particular point to the center. Okay, to the origin. All right, let me draw that. That is one point. I'm connecting that to the center. Okay, and let me try to extend. Right, so this is wavelength to the generator. That's why I'm rotating like this. Is that fine? I reach a point. So now I need to find out what is the wavelength over there, correct? So for that, what I have to do, I'm supposed to, you hold this as a radius, okay? Take this as a radius and draw a circle from here. I'll change the color of the circle. Maybe I'll use say black color. So this is a circle, right? So this is the radius. Take this as a radius and this is the center. Origin is the center. And from this point, you draw a circle. Okay. Now that touches at this point. Right? Just do that. Can you read what is the exact value on your Smith chart? Because mine is not accurate, so I don't want to read this value. This point, what I'm marking now, right? Can you see here? After drawing a circle, the circle intersects the second straight line at a point. We need to read a impedance value over there. 1.8. Well, let me try to zoom. Maybe you are close. Let's see. Okay. So yeah, so 1.8 is, it's actually the x value, correct? It's a, you see, whatever you read here, these values are the x values. I want the r value first. R value comes from where? R value comes from this circle, correct? Yeah, so that is 0.4, it comes 0.4, right? Possible, right? It's maybe this, whatever I'm getting point here, maybe you are getting a point over here, right? Accurate point, right? So, okay. So whatever value you are getting, you tell me, I'll write. So 0.4 you are getting, I'll write. Okay, just a second. Let me. So sorry, the R value is 0.4 and the X value is 1.8 something, correct? Is it okay? Yeah, right. Okay. So let me write that. So what we get here is that. So this is uh, Z equals to 0.4 plus J. How much? What's the X value you're getting? I think approximately 1.8. Fine. That's fine. Okay. All right. So we got that answer, right? The answer for the first question is that what is the impedance at L equal to 0.1 lambda? So your answer is, right? I got a normalized way, right? That is, I'll just write here. I'll just write here. So that is Z at 0.1 lambda. Read that value, 0.4 plus J 0.18. But you see, this is not exact, right? What I am supposed to do, multiply that by the Z naught, because everything is normalized. Multiply by 50. So now you tell me what you get. So this is 20 plus, what is this? 0.18 into 50. 9. Okay, so 9 ohms. That is the answer. Right? So if at all somebody asks a question that if the length of the line is say 0.2 lambda, right? And the question is asked, right? What is the value of the impedance? What you do, instead of moving by just like this, right? This is now just 0.1 lambda, correct? This value is 0.1 lambda. You don't do that. You go for whatever is the length they have asked. Okay, just see whether you have to move clockwise or anti-clockwise, right? Clockwise means towards generator, and if some, yeah, if at all they have given the value somewhere at the middle, and they say that if you move 0.7 lambda, you reach the ZL and find the optimum value of ZL. What you have to do? You have to move anti-clockwise and add a distance 0.7 to that. That's all. Okay, right. Toward okay. So I'll repeat that point. So let me assume that. So you see the value is given somewhere here. Okay, this is the point, not the low, right? At this point, the value is equal to something X. The impedance is X, total Z. Okay. Now they say that if you move a distance of 0.7 lambda, what is the impedance over here? Right? That means you are moving towards the ZL, right? This is the ZL. So you should move anti-clockwise and the distance equal to whatever they ask, like 0.7. Yes. Okay, only that's what I said. Is it okay? Ah. So first part of first part we try to answer. Now let's move on to the second part of the question, right? If you see the second part of the question, okay, let's check what they are asking. So in the second part, question is find the voltage standing wave ratio, VSWR. Okay, so to find the VSWR, right, I need to do one thing. So measure the distance. Okay, you had drawn a circle, right? The same circle you continue, this circle you continue, right? And measure this distance. Anyway, you know that the distance is already known to you. Okay, so I want this distance to be measured, and is it okay? So did you measure that? You hold it. You hold this distance. How much is this distance? Okay, measure it. Maybe anything by using even a scale or whatever, right? So actually, remember one point. This point represents your Z minimum. Okay, not Z minimum, Z maximum. Sorry, because it's towards infinity, right? So this is the maximum amount of Z. So I'll write this where no, it's not a straight line. It's a circle. Sorry, my mistake. Right. So extend the circle. Continue that circle which you had. Okay. So maybe like this. All right. It reaches the it cuts the horizontal line at some point. So that point, whatever you measure over there, is the minimum amount, maximum amount of Z what you get. Okay, on this line, because you know that we have Z max and Z min, right? So Z max is obtained like this. So measure the distance from the origin to that. It's actually the radius only. Okay. Basically, you are trying to find the radius of the circle. Whatever you have as the radius, right? Hold on to that, right? Maybe you measure the radius while drawing the circle. Okay, hold on to that. Keep it as it is. Come down and note that there is a scale given at the right. So can you see radially scaled parameters? In the sense, everything you have to measure is with respect to the radius only. Whatever is the radius of the circle you are drawing, only that radius can be used to measure the various parameters. Now, what are the parameters you can measure? Come here. So the first line, that is right, whatever is marked here, it is SWR, standing wave ratio. Okay, it's a standing wave ratio. So I have, sorry, that means I need to measure something on that particular scale, right? Now you see, if you move this way, it is towards the load. Okay, but now you see you are moving towards the generator, correct? So that means, oh sorry, just a second, I'll back. Now you see, so if you want to move towards the generator, then this is the direction, isn't it? Opposite direction. So from the center, let me, why this is resetting everything. Okay, fine, all right, that's not an issue. So from the center point, you see center point is here, okay? From this point, mark that radius to this side, okay? It may, whenever you measure that, you will read a value on this particular line. Okay, can you read and tell me what is that value, right? Whenever you draw an arc, right? Drawing, keeping, sorry, keeping this as the center, okay? And somewhere here you may cut because that's the radius. When you cut that, what is the value you read? Please tell me. Yeah, that radius. Distance is the radius, okay? Exact same radius. May not be 2.2, but because I have some bigger value here, so I'm expecting something more than 10. possibly. I'm not very sure because mine is not to the scale. But when you do that, you will get according to the scale. So I'm expecting by just looking at the this thing, maybe something. Oh, this scale is not there. Oh, then it's a problem. Okay. Normally, uh, whenever you use a Smith chart, make sure that you have these parameters also, because every problem needs this scale. Okay, because your next question, you see that what is the reflection coefficient? You can see that at the bottom there is another scale that is only, yes, that's only dedicated for the reflection coefficient. Okay, but anyway, that's fine. For the time being, you just make sure that you know how to measure, but later on you draw, once again you use a proper Smith chart and just measure everything. Okay, so equivalent value, I'll take somewhere here. Okay, maybe uh, I'll draw something. Okay, just for your reference, because when I share this notes, you will understand that what you are supposed to measure. Okay, all right. So what I do, I'll measure that on this scale starting from here. I'll mark a point somewhere here. Okay, like this, what I draw, that is my VSWR. Okay, I'll just write maybe 12. Let's see. Okay, fine. Let's go to the next part of the question. Okay, let me check what I have in the next part. So it says that find the reflection coefficient, right? Reflection coefficient means you are going to measure at the load. Okay, at the load, in the sense, this is the ZL. At this ZL, what is the reflection coefficient? So I know that I have a scale. I have to use a radial parameter over there. So I still use the same radius. I don't change it. Okay. But what I do, I'm going to measure the uh, reflection coefficient, right? You see here. Let me zoom it. So reflection coefficient has two things. Okay. You can see on the at the bottom. One is reflection coefficient P, one is reflection coefficient of E or I. So I am supposed to look at the reflection coefficient of E or I, because whatever I'm measuring with respect to the voltage or the current, correct? So what I do, I'm still measuring uh, I'm holding the radius, whatever I have measured earlier, but now I'm placing that particular radius on this one. Okay, on this graph. That's all. It's I'm measuring on the over here. So I'll try to place it exactly like how I place. Its length will remain same. So whatever length you got, it will be the same length. Okay, same to same. But the reading, whatever reading you get, it should be somewhere here, corresponding to this point. So I think it is more than zero point 0.8, but lesser than zero point 0.9. Let me check. Okay, so that is the gamma. It's a reflection coefficient. Again, you will be able to measure only the magnitude. So let me take that as 0.85, somewhere in the middle, right? Approximate. Proper one you measure later. All right. Okay. So that's how I measure the magnitude, right? So from the graph, I am able to measure that magnitude of this is equal to 0.85. But I know that this gamma, whatever we measure, right, that is a complex number, correct? So complex number in the sense with the magnitude, I also need the angle. Is it right? So measuring angle is very simple, right? At the load, this is the gamma. At that load, right, I need an angle. So simply measure this angle with respect to the horizontal line, whatever is the angle made by the line which you have drawn, right, connecting the ZL and the center, right? That angle you measure and tell me how much you get. 126. All right. So what I do now, so that means I'll write an angle. So magnitude of gamma is that. And okay, so this is what I'll write gamma L. So angle of gamma L is equal to 126, exactly 126, is it? Okay, 126 degrees. So I can write that, therefore, the gamma L is equal to 0.85 at an angle 126. Okay, so that is the answer for our which question? Question number 3, reflection coefficient. They are also asking what is the value of the reflection coefficient at L equal to 0.1 lambda. What do? Just see this radius is still same, correct? Since the radius is same, no change in the magnitude. Okay, at Z1, magnitude of gamma is still 0.85. We don't have to change that. Only the angle changes. So angle of gamma is equal to, I can call it as a gamma 1 as well. Okay, just measure this angle, the smaller angle. Bigger angle is 126. Measure this angle. 54. Okay, so that means I can write here angle is equal to 54 degrees. So gamma 1 is equal to 0.85 at an angle 54 degrees. Okay, that's all. So we could answer that question completely. Okay, now all right, right. So this is clear, right? This particular answer. Do you have any doubt? Yes, yes, yes. You will keep the radius same. Okay. Sorry. Can you can you repeat the question? I couldn't hear you. Sorry. I couldn't hear you. Can you repeat? Uh, Bottommost scale. That is called as, that's actually the transmission coefficient. Okay, there are 5 scales. Okay, first scale is SWR, right? Second scale is the loss. Third one is the reflection coefficient P. Fourth one is reflection coefficient E or I. And the last one is called as a transmission coefficient. Okay, if a question comes on the transmission coefficient, we'll be using that. Okay, I think it's not visible here. I'll quickly show you the other side. Now this is visible, right? So this is what are the 5 scales. Okay, right. Fine. So how we got these values, I think that you're fine, right? So on the first, keeping the same radius, measuring the amount of radius we got on the first scale gives the VSWR. Okay. On the fourth scale, we'll get the reflection coefficient in terms of the voltage or the current. Is that okay? Do you have any other doubts? Just verify. Yeah. E and I, E or I, in the sense, if you want to measure the reflection coefficient, right, with respect to the voltage or current, that's the one. Okay, power, if you want, you will go through the one before that, P. Okay. So everything as of now, whatever we study, right, that is with respect to voltages or the currents only. Okay. So we'll be using the first and the this particular fourth scale most of the time. Okay. Right. Okay. So this is the complete answer what uh, we did so far. Okay. Just check and let me know if you have any. Okay. Then I'd like to proceed further. So the next question. Okay. Question number 2 is a similar question, but I want to answer slightly different version of the question. Okay. So this is the question. For a transmission line with Z naught equal to 1, the ZL equal to 0.2 minus J 0.2 ohms. Right? Part A of the question. Find the Z at L is equal to lambda by 4. Then part B of the question. All right. What is the VSWR? These questions are same, but now I'll change the next part of my question. Okay, so this is then part C of the question is how far from the load is the first voltage minimum and the first current minimum. All right. Okay, the first two parts we can definitely answer directly. We just have to mark the points on the line. Okay, so let's calculate. Let me bring the Smith chart once again. All right. So we know that the Z naught value or the characteristic impedance is 1 ohms. So the normalized ZL becomes the same as the given ZL, right? So I don't have to divide by anything to convert. So I can directly write that itself. That is uh, how much? I think 0.2 minus J 0.2. Okay, so just mark that point first on the Smith chart. So I need to trace the R circle, constant R circle with 0.2. So I think this is the circle. All right. That's a 0.2 circle. And I also have to find minus j 0.2. So this is the one. So this is the circle which we are talking about. So intersection of those two circles will be the point. Okay. So 0.2 and minus 0.2. Let me mark that. So that is this point. This is the point ZL. Okay, for our reference, I'll put a X mark over there. Just this is the ZL. Okay. Now, so so first part is pretty straightforward. Anyway, we have marked that. So find the Z at L equal to lambda by 4. Lambda by 4 means it is 0.25, correct? So I'll just write the answer to the first part of the question. So Z at lambda by 4, that is equal to 0.25 lambda. So what you will do, simply connect the point ZL to the center of the circle, correct? That's our first job. So from the center, I'll say that is a center. Draw line to this and try to measure where it actually meets the outermost part of the circle. Is that okay? So that is the first thing that we are going to do. Then let's try to make a measurement. Maybe mine may not be so very accurate, but when you read whatever you get, you tell. So it's more than 0.46, but less than 0.47. So if I, right, so we can see that 0.46 to 0.47 is divided into 5 pieces, correct? 5 parts. So each part will be 0.02 then, correct? Yeah, approximately. Okay, so I'll write this is 0.466 lambda, correct? That's the value I have here. So now I need to calculate if I want to move towards the generator. You have to move towards the generator now because it is the load, right? From the load at a distance of lambda by 4, what is the value, right? So I have to move to a point, right? That is 0.466 lambda plus 0.250 lambda. Because this is what is given is load only, right? They may not mention. You see the question. Transmission line with Z0 has a ZL equal to this one. Find the Z at lambda equal to L by 4 means you have to move from the ZL towards something. So towards means what? I have only one option. I have to move towards the generator. Okay. Is that okay? Why we are moving towards the generator? So what is that value? Yeah, I have to move this direction towards the generator. Okay. And what is the value? When you add this value, right, that is 0.250, what's the value I'm expecting? Zero point 716, I guess, right? 716 lambda. Okay. Now, now I need to observe something that is related to the graph. Okay. Graph has a feature that, so you see here, if I start moving from 0.466 towards the generator. I have 0.47, 0.48, 0.49. There is no 0.5. It becomes a 0, right? It means there is no, after 0.5, I don't have a 0.5 or 0.6, right? You see, once again, it resets to 0. Okay, doesn't matter. I keep counting, right? I need to keep counting in the same fashion, right? So that means I need to calculate the equivalent of the point 0.7, what's the value? 716 on the graph. Now, for example, see, this is maybe from here, this is point, say, point 0, point 1 for me. Let me assume, okay? Point 1, point 2, point 3, point 4, point 5, point 6, point 7 comes somewhere here, let's assume. So, but I don't have a point 7 here, I have some other number. Now I need to find out what is the some other number that is corresponding to, that corresponds to 0.716, right? I need to take care that my 0.5 is, right, 0.5 is how much? 0.5 is 0. 0.5 is 0, 0. Now, yes, yes, yes. Okay. So now what I'm supposed to do, I simply have to calculate point. If I have to move to a point which is equal to 0.716, right? What is the actual distance I need to make? This is the actual distance I need to cover, correct? So you have two things to do, right? One the yeah, can you tell me that is 0.21216? Perfect, right? So how did you do that? Can you tell me which method you applied? Yes, right? Because as soon as it becomes 0.5, it becomes a 0 form, correct? So the distance that I'm supposed to cover in total, the total distance that I'm going to cover, right, will be, total distance that I'm going to cover will be, right, 0.25, 0.25. So corresponding to 0.25, the one point which I reach on the other side will be, right, yes, what you told is right, 0.216. So zoom in and mark the point corresponding to 0.216. All right, that's right. So let's come back to that. So I'll zoom in. On the outer scale, I want 0.216. Okay, so 21, 212. Okay, 21. This is 21246, right? Maybe this is the point what we are talking about. Is it? Am I right? 0.216. Is it okay? So I got a 0.216 and I am supposed to connect that point to the center. That's all. So let us connect. From the center, draw a line that actually passes through that. Okay, mostly this becomes a actual proper straight line from the beginning, right? So I'll just write this point is 0.216 lambda. All right, so far good. All right, what's the next step? I need to measure what is the impedance at this point. So what you are going to do, right? Take this as your radius. Take that as a radius and draw a circle. So take this distance as a circle. Somewhere, I think you may reach somewhere here, I guess. Maybe this is the point which you reach. So I'll try to draw a circle. May not be proper. Let me see whether I can. Okay, once you draw the circle, just let me know what's the point you are reading over there. Okay, because uh, for me, I don't have a proper circular shape coming up. Yeah, until it meets the straight line on the other side. Okay, so I'll just roughly draw. So that means you will start from here, you move around and you touch this. Okay, this point is, you will mark the point after that. Once it touches there, you draw, you mark the point. Okay, yes. Once you read that, uh, tell me how much value you get. This is the required Z value. Yeah, you need to read two things. One is R value and one is a X value. X is a 0.3. May not be 0.3. You see here, it's a bigger value. I'm reading somewhere like 2, 1.8 something. And R value you read from this point, somewhere here between 2 and 3, I guess. Yeah, that's possible. That's possible. Okay. Yeah. So tell me the complete one. First R, then X. Okay. I think between somewhere around 2 and 3. You need to read the that circle which touches the x-axis. Like if this is a point, I can see a circle coming and touching here, right? So it's touching between 2 and 3. So my value is 2, 2 point, 2.2, 2.4, 2.6, 2.8, and 3. So right now I'm measuring on my scale is 2.8. Like that you measure what's the value you are getting. 2.2. Perfect. All right. So that's 0, not 0, sorry, 2.2 plus j, I think you told 2.5 or something, I guess. Right? What is the x value? You get 3.0 plus j3. All right. So that's the z value you get. That is the impedance at a distance of 0. Lambda by 4. Okay. At a distance of lambda by 4, you have impedance equal to this value. Okay, so the next part of the question is find the VSWR, right? What you have to do, take the same radius, whatever you have right now, that radius you use to draw the circle, right? take that and place it on the first scale. Okay, so I'll try to measure that from this. It's somewhat yes, so that is what I think I'm going to get a value equal to somewhere here. Okay, this much I guess. Okay, so roughly this is the VSWR that you get, maybe 5 point something. I'll just show 5. Okay, so the next part is interesting. The next part of the question, let's read once. It says that how far, sorry, all right, so how far from the load, right, is the first voltage minimum and the first current minimum, right? So in order to measure the voltage minimum, right, voltage minimum occurs, right, you know that this is the point of the minimum voltage. Sorry, I'll take up the color once again. On my graph, wherever the you see Z minimum happens, wherever you see the Z minimum, that is the point of voltage minimum. Okay, just remember, right? I need to find out the point, right? So V min occurs at Z min. Similarly, if at all the question is to find V max, that occurs at Z max. Is it fine? Okay. Now, the impedance changes according to this path. Whatever path we have drawn, according to that, we have the voltage, the impedance changing on our line. Okay, I already mentioned in the previous problem that if you want to measure the Z max, right, wherever your circle crosses your horizontal axis on the right side, correct? So that is the Z max. I already marked the Z max. Okay. Similarly, if I want to measure the Z min, I have to see wherever my circle cuts the horizontal axis on the left side. So here, this is the point. Are you okay? This is my horizontal axis. That is the Z min. Right. Now, distance between my current load and this Z min is the distance what they have asked. Okay. Are you okay with that? What is the distance between this ZL and the point where I have the Z min? Correct? Is the first voltage minimum. Are you okay? Right. So what I do, I know that I'll just mark this point. Okay. I'll just mark this point. This is the Z minimum on the line. Okay. So simply extend. I just have to extend the line from the Z min to this. It's actually the same horizontal line. That's all. Okay. Now what I need from the ZL to Z min, what is the distance? Right? You have to move in the clockwise direction towards the generator, correct? From ZL to Z min, what is the distance they are asking? Okay. So the question, if you read, where the first V min occurs is the question, right? If I measure what value? No, see 0.466 to 0.5. That's the point. That's the question, right? Right. So starting from 0.466, I move a distance to reach 0.5. So the distance is 0.5 minus 0.466. That's all. 0.034. So my measurement is that. Okay, so let me mark. No, maximum is different. Maximum is different. Maximum is on the other side. Okay, the other side, wherever the point touches the horizontal axis, that is the Z max. I'll come to that. Okay, because there is a question. The another part of this question says that where is the current maximum? Correct. So we'll do that now. Okay, just a second. All right. So what I do, I wanted to mark a Z min. Z min occurs wherever this circle touches the horizontal axis, right? That happens here. So this is the Z min. So we extend the line from the Z min outwards. So from the Z min, I will draw a straight line like this. And I know that at this particular point, right, the value is 0.5 lambda. So this is the distance between the ZL to the Z min, right, where the minimum occurs. Is it okay? So let's do the calculation corresponding to that. So my calculation is distance between ZL and the first voltage minimum, right, is equal to 0.5 minus 0.466. That is equal to 0.034 lambda, right? At a distance, I just have to move 0.034 lambda from the load towards the generator to get this point. Is that okay? Fine. There is another part of the question which says that tell me the distance, right, of the first current minimum, where the current becomes minimum. Okay, to find the current minimum, right, you see, this is the equation. Current is equal to voltage by impedance. Correct? So current reduces means impedance increases. Correct? So I need to find a point where the Z is maximum. Correct? So that means if you want to find I minimum, that is equal to voltage by Z maximum. So I know that Z max occurs at a point over here, right? This is going to touch this point, right? So what I do, I'll extend that. I know that at this point, its value is equal to how much? 0. Let's zoom 0.25, right? Yeah, outer scale reads 0.25 lambda. So this value is 0.25 lambda. So I already know that from the ZL to Z min, it is 0. How much? 13034. To that, this whole distance, right? The complete distance is 0.25 because it's 0 to 0.25. So I simply can write this part, distance between ZL and the first I minimum, that is equal to, I just have to see what is the origin first distance we calculate, that is 0.034 plus 0.25. Okay, so that is 0.284. It's not minus because I started from ZL, right? I keep moving towards the generator, right? You keep moving towards the generator. Okay, the subtraction will come into picture only when, right, you are moving in other direction. Okay, whenever the directions are, yeah, till 0.25. Okay, so from 0.466 to 0.5, this is 0.02034. Okay. Then starting from 0.5, right, which is equivalent to 0, you have to move till 0.25. Okay, so that is a addition of 0.25. So 0.25 means that's the, okay. Yeah. So just see, do you have any other doubt? And let me know if you have any doubt.